In computer science, we are often concerned with the running time our algorithms take. So we don't usually measure it in seconds or minutes because that's unreliable, and different machines might have different hardware, and even on the same machine, if you run an algorithm once, you might see 50 milliseconds, and if you run it a second time, you might see 45 milliseconds. So there's some randomness that's associated with measuring in just seconds or minutes or milliseconds alone. So we usually want to talk about running time in terms of the number of steps that a given algorithm takes. So say we have some kind of piece of code that or even let's do a example at a high level. We want to look at this array of two elements, and we want to sort this array of two elements, and eventually we should be able to get 1, 2. Now there is a large number of sorting algorithms that different people have come up with, and we can use any one of those to tackle this problem. But if we sit down and compare any two of those, how do we know what's better than the other? Well, we'll take a look at the number of steps they take, and maybe that gives us some information about what's better than the other. Well, not necessarily at this level, right? So say we have some kind of clever algorithm to sort it, merge sort. Let's say we use a clever algorithm to sort this list of two elements, and we have this algorithm called merge sort, which is much more clever than this other one. Silly, or I shouldn't say silly, but less clever algorithm to sort it, which is bubble sort. All right, so we have these two algorithms. Now we sort it using merge sort and we get 1, 2. We sort it using bubble sort and we also get 1, 2. But we don't see a huge difference in the number of steps it took for merge sort or bubble sort. So how do we know which one's better? Well, merge sort is certainly much better than bubble sort, but we can't really tell with an example this small because maybe both of them just took 1 step or 2 steps, and we can't really even tell what's the better algorithm here. And that's why it doesn't make sense to talk about small input sizes. In fact, we want to look at the asymptotic behavior of as we get larger and larger input sizes, what kind of running time do we see in terms of the number of steps it takes for large and large input sizes. So from now on, let's just let n denote the size of our input, right? So as n gets larger, or in other words, as the size of our input gets larger, merge sort performs much better than bubble sort, it turns out, right? But we would have never known that with just 2 elements. So that's why we talk about asymptotic behavior of this when we talk about overall running time. We want to look at asymptotic behavior, and closely tied to that are these 3 notions of big O, big omega, and big theta. So first of all, before we talk about any of those, we want to take a look at what it means to even talk about steps. So what do we mean when it took this many steps to execute a function or execute some kind of program? So say we have this example of a program which has for I in n, or range n, and for j in range n, say we have that we want to make it do something. So this do something, how many times will it do this same something? Well, you can see this is just like a summation, or rather, I should say, it's it performs something n times, and then it performs the n times something n times. So it's n times n doing something, right? Or rather, it has n squared steps, and it does n squared times it does something. So in this case, we said it has n squared steps. So with respect to the input size, it has n squared steps, or that's how we described our running time. And now that distinct number of steps describes a distinct family of functions. In fact, it describes the quadratic family of functions. So stuff that looks like y equals n squared, or even y equals n squared plus n plus 3, maybe 5n, and maybe this was 195 n cubed, right? So this is what it means over here for this being in the quadratic family of functions. And we remember it sort of from calculus class and high school math that some functions grow faster than others with respect to this independent variable. In this case, we have our independent variable n, right? So that's our input size. That independent variable n dictates how fast the function grows, and maybe a log function. So y equals log of n. This grows much slower than this quadratic family of functions, right? So there are different families of functions which have some distinct behavior of growth. And what we're interested in is which family of functions are we taking a look at in our algorithm. So which family of functions does this belong to, or what family of functions does our algorithm correspond to? And this is where we look at big O or big omega or big theta, because we can talk about big O or big O, and this refers to the upper bound on the running time of our algorithm, right? So if we say some function f of n, and this f of n might look like n squared or n cubed or whatever based on the code we see, based on our algorithm, whatever that f of n is, f of n is in big O of g of n. It's in big O of g of n, and this implies that there exists, right? There exists some c and some m such that, or I should say c and m greater than 0 such that, right, c times g of n is greater or equal than f of n. But that need not be always the case, right? It's okay if this f of n is larger than g of n times c at some point, but eventually this will be the case. So this is whenever we have that n greater or equal than m, right? So this is asymptotic behavior right here. Asymptotic, it means whenever n is greater or equal than m, this is going to be true. It need not be true all the time, especially in particular when n is less than m. It need not be true, but it could be true, but it need not be true. Although whenever n is greater or equal than m, this has to be true for this to be in O of g of n, right? So if we take the contrapositive of this implication, we can say whenever n greater or equal than m, if we have that c times g of n is less than f of n for some c and m greater than 0, then f of n is not in O of g of n, right? So if it is in O of g of n, then there has to exist these c and m greater than 0 such that this is true. Okay, so that is talking about the upper bound, and in this case g of n is some family of functions like a quadratic or something that should be growing faster than f of n, which might be something like log, or even if they're both quadratic, then this would be the case where they're equal like this. But if it's greater or equal, maybe it's greater than, strictly greater than, if f of n is something like log, and if g of n is something like quadratic or factorial or cubic or something like that. But in general, we say greater or equal than. So we saw that this is describing the asymptotic behavior here for this upper bound. We can similarly describe the asymptotic behavior for a lower bound using the big omega. So this omega symbol right here is what we're talking about. The big omega refers to the lower bound on the running time of our algorithm. So we say, so f of n is in omega of g of n implies that there, actually I can even copy paste most of this because the definition is almost identical with the exception of this inequality. If this inequality is flipped, then this is precisely the definition of lower bound, of being lower bounded by this family of functions. So there exist c and m greater than 0 such that c times g of n is less or equal than f of n whenever we have that n is greater or equal than m. So again, this is asymptotic behavior we're talking about. N has to be greater or equal than m for this to be true for sure. It need not be true when n is less than m, right? And now, if we see that it is the case that we have both of these, we have big O and we have big omega, and both these big O and big omega conditions are true, and f of n is in this family of functions and f of n is in this family of functions, then precisely we can say that f of n has to look something like quadratic all the time, or f of n has to look something like log all the time, right? And that's because we say that we kind of describe big theta bound, the big theta bound, or we say it's tightly bounded, refers to the tight bound on the running time. So f of n is in theta of g of n implies that f of n is in omega of g of n, and f of n is in big O of g of n. So it's in big omega of g of n, and if it's in big O of g of n, then it's theta bounded. It's in theta of g of n. So it's in this family of functions of g of n that that are pretty much identical to f of n. So what I mean by that is g of n in this case should look something identical to f of n. And you can think of it kind of like squeeze theorem, sort of, because you can take a look at, okay, if g of n is, or I should say, yeah, this might be a little, yeah, okay, you know what, it should be okay. We can think of this kind of like squeeze theorem, and except that we aren't converging to some kind of limit, but rather we're just talking about something being sandwiched between these two functions or these two families of functions. And it turns out for it to be sandwiched between these two family of functions, then it means that that function is kind of identical to that g of n, right? It has to kind of be identical to, it has to belong to the same family for it to be sandwiched between them. Otherwise, if it wasn't from the same family, it would be either able to, you know, break that lower bound or break that upper bound. But because it's precisely sandwiched between them, it has to be in the same family of functions. So hopefully that didn't confuse you, but like I said, if you keep the intuition in the back of your mind that it kind of seems like squeeze theorem, and kind of seems like the case where we have two functions sandwiching a function in between, but this is not sandwiching a function in between by two functions, it's a family of functions, two different families of functions, or yeah, two different families of functions squeezing a particular function between them. Kind of resembles squeeze theorem in some sense, except that we're not talking about one limit, but rather we're talking about overall just the behavior of these functions, because yeah, that's really all we're talking about here with the asymptotic notation. Maybe I shouldn't have talked about squeeze theorem, but I don't know, it just made sense for me to throw that out there, maybe to give some intuition behind what this is trying to say here. But basically, we talked about how big O talks about the upper bound, big omega talks about the lower bound, and big theta is referring to the tight bound whenever we see that f of n is in big omega and it's in big O, then it's in big theta. And maybe that was more confusing than it should have been, but hopefully it makes sense. And there are a lot of practice questions, and there's a whole branch of computer science concerned with algorithm complexity, and it's very useful stuff depending on what kind of work you're doing. And so hopefully if you try some of those practice problems out on maybe the old CSC 236 website, then it might make a little more sense. So I encourage you to try those, and hopefully it'll all be clear. Thanks for watching.